Last time, we started talking about applications of solar energy and basically focusing on the thermal energy, applications. And today also, almost the entire lecture, I will focus on thermal energy. And in the subsequent lecture, we will move on to the light from solar energy and how that is utilized. Okay. Uh, last time we went through the equations for a parabola, all right? And I showed you parabola troughs, which can generate very high temperatures because it all focuses on a line. I mean, that's what happens. Now, this is actually a parabolic dish. Okay, so it's again a parabola, all right, and it focuses on a point. And now this is very extremely useful. Okay, you can see what is the relationship between the focal point and the diameter and the depth of the reflector. Okay, I mean that's the relationship. Okay. And now, so what happens is that with this, you can easily generate temperatures in excess of 100 degrees centigrade. And so it's very good for cooking, community scale cooking. And in fact, you can see this lady basically keeping all the pots and pans for cooking, community scale, and the entire cooking is done with solar energy. Okay, so this is again a great application of solar energy. Many places they have actually set up such units, for community scale cooking. Now, just so that you also know that there is obviously when I am able to generate high temperatures, I can naturally generate steam, and you can generate good quality steam. Like for example, here you will see that the operating temperature is about 173 degree centigrade, and they get that at a pressure of 8 bar. Okay, and a large number of these troughs, are there. Okay, it's in Egypt. Okay, and this is a pharma company, and this pharma company actually draws almost all of its steam requirement, for as process heat through solar energy. Okay, so this is a parabolic trough setup. Now it's interesting that in the same place in Egypt, they had actually put up one of the earliest parabolic troughs, 1913. It was put up by two Americans. Okay, and so I mean at that time, of course, they were using it for pumping of water, and so they were able to use things, even at that time. I mean, what about 110 years ago? Okay, and so there's no reason why, let's say today, you cannot do something like that. Okay, obviously the technology would have been even more advanced, today, and so this actually was set up in 2005. So around there, that they had set it up. But it's interesting. You can see how actually steam is generated. So these are the parabolic troughs, and from the center you have a tube, through which you pass water, and that water is what is getting converted into steam. Yeah, and you can see it better over here, like you can see how steam is coming out. Now you feed it in one of these. You can't see yeah, you can see over here. This is the tube through which you pass water. Okay, and that is you can also have many of these in series, so it goes from one, it goes to the other, and that's how you build up the temperature. Okay. And for example, this is an application where it would be very useful for a place like Nagpur, where there's a lot of orange cultivation. From the orange peels, you can get out this oil, limonene. It's extremely useful. Okay. And to take it out, actually you do a steam distillation. Okay. With this, and that whole thing you can actually do using this kind of steam from the parabolic trough. Okay. So another good example of where it can be used. Now, when we talk about it, and I, of course, will not be going into all those details, simply because it would be too involved. But what you need to understand is that one is, I can operate these things without too much of very fundamental knowledge, except for the fact that a parabolic trough gives you a concentration of solar energy. But if you really want to optimize the system, then there are, of course, you need to know many of the parameters, like what is your average insolation, okay, what is your ambient temperature, okay, what is the wind velocity, right? And so those who are good in modeling, all right, what they will do is that there are standard equations, which have been set up, where you can feed all these things, and you'll get some idea about what is the kind of steam, etc., that you are likely to be able to generate. Okay. And so what will be your production? So you can see, I mean, this of course is a small experiment. There's 410 gram of orange peel. What is the moisture content? How much is the water taken in the absorber tubes? Which becomes steam. What is the amount of oil that you finally extract? And so you will have to actually compare all of this data. And whenever you're doing work with solar energy, remember that solar energy tends to vary from day to day, not to speak of from season to season. Okay. And within a day, as you know, from hour to hour, and we have gone through those equations of solar noon and everything else, from which you can get an idea of what kind of insulation you will get. So it's very important that one tries to see what is the variations that you get. Let's say, see, this over a period of several days, this data was collected. Okay. But you obviously need to collect it over much longer periods of time. And and depending on the type of behavior day to day, many times you can also get fairly large variations in the for example, the oil yield, you can see is varying a lot, from 2.51 to 9. Okay. So and here you'll see that generally the insulation is high. This is the watt per meter squared. Okay. And maybe what happens sometimes is that your wind velocities can also vary, and that can also significantly affect your results. Okay. So I mean, I'm not going to go into the detail except to ask you that what would be the typical kind of things that you will look for. Okay. What are the variables? Okay. Just a better blown up picture so that you can understand that So you can see it's coming from here, like let's say, and it's going here, okay, and it's increasingly getting heated up. Okay, it's going this way, and so that's how. By the time you come exit from here, this. By the way, it need not be only water and steam. For example, many times what happens is that if you are indoor, okay, suppose you are in your kitchen, all right, and where will you get this solar energy from? I mean, if for example those people who have got terraces, like in the Middle East, they've got so much of sunshine, they can set up these things in their terraces, okay, and what you can do is pass hot air, and so you'll end up getting very hot air, and you can pipe that hot air into your kitchen, and you can do the cooking there, okay, using hot air. All right, hot air as basically the heating medium, so this is actually very, very useful, hot air, because it's easy to transfer from one place to another, and I mean within a small distance, of course, and uh, keep this in mind. It need not be water; it can be oil, and you get hot oil, or it can be water, or it can be air. Any of these things which can be heated up and which can serve as a heating medium. Okay. Now let us look at a very different kind of an application of solar thermal energy. It's still solar thermal energy, okay, and for example, this is an application in refrigeration. Now, this would be great. I mean, like many places, where, let's say in farms and all, they're producing vegetables, and it's a perishable. So you need to, you'll see that so many of our things today are put in cold storage. Okay. And so you could actually run cold storages with a refrigeration unit, which is basically based on solar energy. So let us try and understand. In fact, the first, I've shown you the picture of the first such unit, which was set up in India around 1978 in Baroda. Okay, and this was, of course, not a very efficient system. Maybe you could get about maybe around 10 to 15 degrees centigrade kind of a temperature, in the cold storage. Okay, and now you can, of course, make it much better, and by using concentrated radiation. Okay, so let me explain to you the operation of a typical refrigeration cycle, and effectively where how exactly the solar energy is coming in. Now, what typically happens is that what are we trying to do when we are trying to get a low temperature, a cold storage. Okay, so obviously, let's say this room, the air would have a certain temperature. Maybe it's quite warm. If it's in Baroda, it might go to 40 degrees centigrade. Okay, temperature. Okay, so and that's what you're trying to cool down to, let's say, a temperature of 10 degrees centigrade or 15 degrees centigrade. Okay, so you need, to something which will obviously take away the heat, right, from here. And what you need is something, like let's say this is a liquid, okay, and this liquid is ammonia, and ammonia has a boiling point of minus 33 degrees centigrade, so obviously anything, this would be very hot, and you can it would take the heat from this, from the room, okay, and it will evaporate the ammonia, okay, and effectively vaporize it. Okay, so And even if you are at, say, a temperature of 5 degree, and you want to go to, let's say, 0 degree centigrade, it's possible to do it here, because yeah, the more of that, the ammonia can evaporate even at 0 degree centigrade temperature, because its boiling point is low. Okay, and so it will vaporize. Now, ammonia also has a reasonable latent heat of vaporization. So, from a, let's say, from a certain amount of the liquid ammonia, you can uh, heat up a lot of the, or exchange a lot of the heat from the surrounding with a small amount of ammonia. Okay, let me just check. Um, I'll just see if I can get any data on the latent heat. It's here. So plus 23.35 kilojoule per mole. Okay, that's the latent heat of vaporization. Okay, uh, so you know, yeah, standard enthalpy of vaporization plus 23.35 kilojoule per mole. Okay? So let's put that thing down over here. Okay, uh, of ammonia. Okay, so and by the way, this is something that you all must be able to pick up, that what is the relevant information that you require. Right? If the latent heat is too low, then of course I would require very large amounts of the fluid. So you need to have something which has got a reasonable kind of a latent heat. So this is not too bad a figure. Now we will go through the cycle, so that you understand. So you can imagine that there is an evaporator, so it's evaporating the ammonia which is in a liquid form. Okay, and this is getting cold. Okay, and it can keep cooling down because the boiling point is low. Obviously I need to keep this liquid at that kind of a temperature. Okay, so that's important. Okay, now then when it says evaporator, and it's a liquid, obviously this liquid must be at a reasonable pressure. It is not actually necessarily at one atmosphere pressure, because then it will all boil away. Okay, so there would be some amount of pressure under which the ammonia might be present here. Okay, now that ammonia which is vaporizing, what happens is that you need a medium which will then soak it up. Okay, and so that provides the driving force. Otherwise, if the pressure just builds up here, then this evaporation will stop. Okay, so what I need is, I need to absorb that ammonia, and the ammonia water is a very good system. In other words, water can absorb a lot of ammonia. Okay, and so you are putting in your ammonia, and because the ammonia is getting heated up because of this, taking up the heat from the cold space. So what you do is that you let go of that heat. So you have some kind of a cooling water, which is circulated. Okay, and what that will do is that by lowering the temperature, the more you cool it, the more ammonia will absorb in this setup. Okay, that's effectively what you're doing, and you're driving this evaporation of the ammonia. Okay, and then you have taken away the heat, so it's at a fairly low temperature, and this cooling water I'm talking about is not extremely cold water, whatever water is available with you, you use to take out the heat. Okay. Then what you do is that with the help of a pump, you pump this whole thing, okay, and you take it into this particular system, okay, over here, which is known as the generator. Okay. Now you will see that it shows solar energy. Okay. Now, what is happening is that ammonia is in water. Okay. Now, and ideally, the hotter you can make it, the better it is. So, this solar energy, ideally, if you can put it like a concentrated device like parabolic trough that I told you, or a parabolic dish, those kinds of concentrators, then you can get very high temperatures here. Okay. And that's what you want. You ideally like a temperature of maybe around 150 200 degrees centigrade if possible. Okay. Make it as hot as possible. Okay. Now what then happens is that because it's a liquid, but the ammonia is quite volatile, as we know. Okay. So the ammonia will start evaporating. Okay. And not just the ammonia, some amount of water will also evaporate when it gets very hot. Okay. And that depends on what is the temperature of this heat input, what is the T, for this particular thing over here. So, and of course, ammonia will be much more volatile than water. So the ammonia will preferentially evaporate. Most of the water will collect here as a liquid. Okay. But some amount will, of course, along with the ammonia, it will form vapor and it will go into a rectifier. So a rectifier is where you'll do a fractional distillation. Okay. So what you're doing is that ammonia, is going to come off, over here, and your water, is really going to basically be returned over here, and your ammonia. So it's like a liquid vapor system. Okay. And so your ammonia is going here. Now what will happen is that because I'm applying a lot of temperature here, and the space is restricted, so the ammonia will get increasingly more pressurized. Okay. And its pressure will build up. This whole thing is a closed system. Okay. So it's getting pressurized. Right? Now what happens to the boiling points of liquids when you increase the pressure?
Boiling point increases.
Right. So what it means is that because the boiling point increases, that as I increase the pressure, there will be a tendency for the ammonia to liquefy. Okay. But on its own, it doesn't really do it. Okay. I build up very high pressure, but it's still a vapor. So now what I do is that, the heat, because it's all hot, the heat is getting basically radiated to the environment from here. So this is another place where heat is going out of the system. So make a note of where heat is going into the system and where heat is coming out of the system. Here heat went out, here heat went in, here heat went in, here heat went out. Okay. So as the this thing is getting cooler and the pressure of ammonia is high, so it will start liquefying. Okay. And so it condenses, all right, into a liquid. Okay. But there is also a significant amount of vapor. It may not be all liquid. Okay. There will be liquid in contact with some amount of vapor, but there will be no water. That's very important, that the rectification here must remove all water and only allow the ammonia to pass through. Okay. So this is, this unit that I talked about, the the rectifier, it's also known as a defligmator. Okay, and it's a device which basically allows you to partially condense, one of the vapors from a multi-vapor stream. Okay, so in this particular case, the multi-vapor is water and ammonia. Okay, so part of it will condense, the water will condense, and the ammonia will effectively pass on. Okay, and and once it kind of radiates, it leaves all its heat, then it starts cooling down. Obviously, you can imagine that if, for example, my system is such that my environment is very hot, then of course, it's not going to take heat, because obviously this has got to be at a substantially higher temperature than this. Okay, and so that's also the reason why it's very important that you put in solar energy with the maximum temperature that you can. Okay? Because if it's a very modest temperature, then the heat transfer from here to here will be poor. Okay? Now you have got liquid ammonia, which is mostly liquid and with some amount of vapor. Okay? And here, what you do is that this is an expansion valve, right? So what you're doing is that over here, your ammonia is under pressure. Okay, and that's why it's in a liquid state. Otherwise, it would have been in a vapor state. If it was if it was at a low pressure. So obviously, because it's at a high pressure and hence it is liquefied once the heat is removed. Okay, now this is known as an expansion valve. So what it does is that it expands the liquid into vapor, but not all of it, partly. Okay, and so what happens is, in other words, the expansion is effectively releasing your pressure, right? Your pressure is now getting reduced. Okay, now, and so you formed a lot of vapor. Okay, and that vapor is of course straight away going to go into this absorber. All right, that vapor. Now, what happens is that this is where this also comes into play, that to vaporize, I need energy. And this is an adiabatic system over here. All right. I'm just doing an expansion and I'm converting some of the liquid into vapor. Okay. And it is drawing heat in the process. Where is it drawing the heat from to vaporize?
Latent heat of vaporization.
Yeah, where is it getting it from? This heat.
It uses
Huh?
its own sensible heat.
Yes. See, it will take the heat from the ammonia itself, the liquid ammonia. All right. And so part of it is now vaporizing, going off, which will get absorbed here. And the rest of the ammonia, because, some of it has evaporated and it has drawn the heat from the ammonia. So the ammonia becomes very cold. You understood? Okay, and it can reach extremely low temperatures, because it has drawn. And that's the, in anything you have seen, if you, for example, suppose you're sweating, okay, and you blow on that sweat, and that vapor is going up, and what happens to your skin? It feels a bit cool, right? Does it feel cool or not?
Yes, sir.
Yes, sir.
Yeah, why
Yes.
does it feel cool? Because it took the heat from the skin. Okay, in evaporating, right?
Yes, sir.
And so the same way, the vapor, the expansion obviously will lead to some amount of vaporization. The vapors will get absorbed here, all right, and the rest of it now becomes cold. obviously it has to be at a sufficiently low temperature so that heat can be taken from my cold storage. And so if I want to, let's say, reach a temperature of 0 degrees centigrade, naturally this has to have a temperature which is lower than 0 degrees centigrade. No? Otherwise, why should it take heat from here? Initially, there is no problem while this is warm. Suppose my cold storage is quite hot and I'll cool it down maybe about, say, 20 degree, 15 degree centigrade temperature. But if I want to cool it down to something like 1 or 2 degree centigrade temperature, then this has to be at a temperature substantially lower than that. Then only heat will flow in this direction. Huh? Heat will always flow from a hot body to a cold body. Right or not?
Yes, sir.
Okay. So the expansion valve plays a very crucial role. Okay. This is really what allows the ammonia over here to be obtained with a very low temperature. Okay? And so much so that now I can draw heat from the space that I'm trying to cool. Okay, and the system process just repeats itself. Okay, likewise over here what you do is that, you see, because this whole system is under pressure, because of this thermal energy, so even the water is pressurized because of this. So what I do is I have another expansion valve because now the water is quite hot. Okay, the ammonia has gone off, but my water will be still quite hot. Okay, so what I do is I do two things. This is hot water. Okay, now this stuff is my cold stream. Okay, and I'm trying to heat it up, so there will be a heat exchange between this returning stream of water and this outgoing stream of ammonia water. Okay, so this is how you warm it up. So part of the job of heating it up is done over here, and this is known as the regenerator. Okay, and this is in the meantime getting a bit cooled. Okay, because of that, but that cooling is also not enough. It's still under pressure, so I do an expansion. I have an expansion valve, and now I can again lower the temperature of the water. There will also be a small amount of ammonia because there will always be some dissolved ammonia, okay, in the water. It will not be absolutely pure water. So whatever is that residual amount of ammonia and the water, that goes through an expansion valve, and because of that now there is another cooling that takes place here. And so I want to obviously return this system to a fairly low, I mean a state where it's not too hot. Okay, and whatever residual heat I'm trying to take out, I will take out with cooling water. Ideally that's what one will do. Okay, so this is effectively how, it sounds strange that I'm using heat energy to actually make something cold. Okay? And now in our refrigerators, what are we actually doing? What is the difference? Can anyone tell me what is the difference between this system and my refrigerator? What is the difference? Well, in the refrigerator, what happens is, obviously I don't have solar energy and this, that. So instead, the whole thing is done by electricity. Okay. So what do you have? You have a compressor. So the vapors, it need not be ammonia. It could be based on CFCs or other things. Okay. So the compressing that you're doing here you're doing it by increasing the temperature, and pressure is increasing as a result. Okay. And you're throwing out the heat. In a refrigerator, what you will do is that I will use a compressor to compress the ammonia so that it, or the whatever is the refrigerant, so that it liquefies. Is that clear now? Everybody understood?
Yes, sir.
Yes, sir.
Okay. And another thing, for example, Professor Bhagwat, he's set up one such ammonia-based unit in one of these milk companies, Gokul Industries. Okay. And only thing is that he probably thought initially he'll run it through solar energy, but probably it wasn't so efficient, or maybe the insulation wasn't that great. And so what he does is that, or this company, they burn biomass, and generate heat. Okay, so basically I can supply the heat by whatever means. I need not, I can do it by solar energy, or if I've got waste biomass and I can burn it and I generate heat, I can do that also. But there's a world of difference, because here you're doing it in a carbon neutral way, right? There is no CO2 generation. Okay, so that's the beauty of this particular system. So I would say, these are very useful devices, and maybe, those who are interested can look up more, on these systems. There are also many other refrigeration cycles. I've only shown you the ammonia water, where ammonia is the refrigerant and water is the absorber. Okay, that's why it's called a vapor absorption refrigeration, because the vapors of ammonia are being absorbed by the water. Okay, so that's the vapor absorption refrigeration system. Okay, has everybody understood the ammonia absorption refrigeration and the role of solar energy?
Yes, sir. Yes.
Okay, okay. Now you can do something quite similar, okay, uh, and you can actually do it not very different, except that instead of absorption, you can also do it with adsorption. Okay? And in fact, these systems, I find a lot of such devices now in Germany. By the way, this unit was actually made in India. Okay, yeah, and these units were actually at that time developed for things like, transporting vaccine, etc., which obviously, you need to keep under low temperature. You know that like these Pfizer vaccines and all, they need to be kept at very low temperatures. They are not even talking about that, but even the AstraZeneca vaccine needs to be at a reasonably low temperature, and to transport it from one end of the country to the other is not easy, and maintaining low temperature throughout. Again, not very different. There is a refrigerant, like in this particular case. Again, I've shown it to you with ammonia. Okay, there is an adsorbent. The adsorbent is, say, zeolite. Okay, and zeolite can adsorb ammonia. Okay, and then and the two processes are adsorption and desorption. Okay, that's all there is. Okay, and like you found in the other case, I mean, ammonia is being taken up by the absorber, and then again ammonia is being released from the absorber. Okay, so that's all. So over here also similarly, you're doing an adsorption and a desorption. So so you can, for example, this is let's say the point A. Okay, so this point. Okay, so what are you doing? Over here, now I have got a, let's say that temperature is quite low, and my adsorbent is initially quite cool. Okay, all right. Now what happens is, and the ammonia, quite a bit of ammonia is actually adsorbed in it. Okay, it's already there, a lot of ammonia. Now what happens is, during the daytime, okay, this thing will heat up. Okay? Now when it heats up, then the ammonia is going to basically get released by the system. Right? Now, because over here the volume is confined and ammonia is keeping on getting released. Okay, so what will happen is pressure will build up and it will liquefy partly. Okay, and as you heat it up even more, you'll collect quite a bit of ammonia, right? So I've gone from A to B to C, right, over here, and I have more or less stripped off all ammonia from my adsorbent, okay, and it's gone here. Now, then what I do is that this part is, let's say, suppose I've got a vaccine box, okay, and which a cold box, and that's what I need to have cold. So this part will actually be in that, that cold box, and now what will happen is it will draw heat from that cold box, okay, which is not cold, and I want to cool it down, okay, and again, it will evaporate. Now the direction will be this, okay, it will evaporate and now it will start, and the temperature is beginning to drop, okay, let's say different times of the day, right? And so now the temperature has got lowered, okay, now this is, I'm heating it up, the my box is becoming cold and my ammonia is again going and adsorbing over here. And the more my temperature goes down, like let's say in the night, when it is reasonably cold, even in very hot places at night it can get quite cold, okay, and so all the ammonia basically reverses and comes back here, and it's like I just have to restart the whole cycle, okay. And this, for example, is done in the zeolite 13x system, okay. But effectively, that's the way in which you are doing things, okay. Is that clear? And in fact, what you can actually do, in fact I didn't show it, you can also it's not just ammonia, you can actually have water which is adsorbed, like that. If it is like a zeolite 13x, you can have water, which is adsorbed, okay, and that water will get dissolved, and that ammonia can basically form like a ammonia water solution, and so I mean you can play this in different kind of ways, okay? Now let me go to the next thing, and this has been, today in the world over, the biggest talk is on solar power, and and I think that everyone is, if not everyone, a lot of people are banking on really the solar power, and of course one is the solar photovoltaics, which I will talk to you about maybe in next week's class when we start solar photovoltaics, okay. But today I will focus on the other option which is being looked at, which is solar thermal power generation. Okay, so both things are being looked at. One is to convert solar directly into electricity, where actually you are making use of the light in the solar radiation, okay, to excite silicon and take it from the valence band to the conduction band of the silicon, and that's how current will flow, which we will discuss next week, right? But in this particular case, what you do is the same thing which we have already seen. Effectively, that I mean, what runs turbines in a conventional power plant? What runs the turbines? What is the source of energy that runs the turbines? Steam, right? Huh?
What is the source of?
No, no. You have steam, right? In most of the power plants,
Yes, sir.
right? It's the steam which is being used to run the turbine, right?
Yes, sir.
Yeah. So we saw that with those parabolic trough, etc., that you can generate fairly high temperatures, and so you can make steam. Now, if you of course didn't know too much, you would say, yeah, fine, I'll with that steam I'll run the turbine, okay? But we will see what is the relationship between the steam temperature and the efficiency of power generation, okay? But if whichever it is, I have to have a parabolic trough collector, you know, uh, and the direct solar radiation is falling on that, okay, and it is becoming concentrated solar radiation, okay. That's what we found because parabolas will always focus at a point, okay. So I can have a very high capture area, like let's say 100 meters squared, and it is finally focused, let's say, on 0.1 meter squared, okay, or 1 meter squared area, which means that I would have a concentration factor of 100. Insulation falling over 100 meters squared is finally getting focused onto 1 meter squared. Of course, there will be a lot of losses, of various kinds. If I ignore all the losses, then that's what I'll have. It is captured over 100 meters squared, focused onto 1 meter squared. So my concentration factor is 100. Okay. Now, we know, we had mentioned this to you in the last class, okay, that you can only concentrate the direct radiation, okay. We know that the solar energy as we see it has two components. One is diffuse radiation, which means that the solar radiation actually got scattered by all dust, dirt, moisture, in the atmosphere, okay, and it became diffuse. And it lost its beam-like property. And the other part will be that the portion which did not get scattered, which is what we call direct solar radiation, only that part you can concentrate. You cannot concentrate diffuse solar radiation. What it also means is that if you are trying to set up a unit, like let's say somewhere in India, you say, I'm going to set up a solar concentrator, you better know what is the kind of ambient atmosphere that you have, and if it is very dusty, and you measure the direct radiation and the indirect radiation, this looks like something that I can do. Like, for example, in cities, where there is so much of pollution, so many vehicles, and all the soot and everything is going into the atmosphere, you would expect that the direct radiation percentage would reduce because of that. So it would probably not make much sense to set it up in a city like Mumbai. You know. But on the other hand, if you go to some rural areas, where there is very little of activity, and the air is nice and clean, maybe the direct radiation would be good there, and you might say, yes, this is the place where I'll set it up. Okay. So obviously, then it is concentrated, and then basically you are generating pressure energy in the form of steam. Okay, high pressure steam. Okay, not low pressure steam, high pressure steam, and because of that high pressure, you are effectively converting that into the kinetic energy of the turbine, right? And from there, you are basically by electromagnetic induction, you are generating electrical power. That's what you are doing. Okay, so that is one of the options which is being looked at very actively today. I will say that the photovoltaic probably has uh, come out more attractive, at least judging by the number of units that are coming up all over the world. The fraction of them based on solar thermal energy is relatively low. Okay. Now, another thing that you need to understand is that, when you are talking about power generation, okay, uh, you you will not necessarily use water and generate steam directly. You may actually pass a thermal oil, which let's say I can heat to, which is stable up to let's say 400 degrees centigrade. And what I will do is that I'll design the system such that the exiting oil, will be at a temperature of something like 400 degrees centigrade, and then I will use that in turn to heat up water and form steam. Okay, so that's you'll do it indirectly rather than generating steam here. The reason for that is, because over here, if you try to generate a very high temperature, you can imagine that you can have ruptures in the system. All these lines will have to be high pressure. So there are complexities in doing that. So it may be better to pass and generate a very high temperature oil, and later on, in a more standard setup, to use the heat from the oil and heat up the steam. Okay. Now, it is very important that we understand that you can say, yeah, I can run a turbine with steam. Okay, yeah, you could, but if you, for example, take a coal-fired power plant or a natural gas-fired power plant, you reach very high temperatures, from the combustion of coal or natural gas, and so the steam that you get is at a very high pressure. So you get high temperature steam. The higher the pressure, higher will be the temperature of the steam. Okay, and so you can actually reach conversion efficiencies, thermal to electrical conversion efficiencies of the order of around say 30%. In a power plant, if you have supercritical power plants, there are certain power plants which are there where you can go up to efficiencies as high as 40%. But temperature plays a very crucial role. So you can see, like for example, if let's say I've got a solar work now, somebody can show you the operation of the solar concentrator, let's say reaching a temperature of 1600 degrees centigrade. But when you look at actually what is the operational temperature, if you take across the operating period, what you might find that it is more like say 480 degrees centigrade. And I'm talking about a situation where you are able to reach a peak temperature of around 1600 degrees centigrade. Now we'll see how complicated that is. And with that, like let's say if I have to generate power, I will be at an efficiency of around 18.4%. That would be a efficiency. Now, as I go lower in the temperature, 800, 400, 200, 100, you can see that the efficiency drops off drastically. All right. So, I mean, it would not make any sense to generate, let's say, if I'm interested in solar thermal power, I ought to be looking at temperatures of this order, at least, somewhere at least around 1000 degree peak temperature, so that I can reach a temperature of around 300, 350 degree centigrade as my operating temperature. Because if I don't, what's the point in doing all this and then having a thermal to electrical conversion efficiency of about 5%? So it would not make much sense. So let us try and understand uh, how exactly these high temperatures are achieved. Um, what should we do? So we are passing let's say an oil, okay, and I'm trying to reach a temperature of say 400, 500 degrees centigrade, or it may be some other medium which I'm using, and I'm trying to reach a temperature of say 800 degrees centigrade. Okay. Now, what should we do? I mean, now once the solar energy has got concentrated, okay, then what is the next thing? What should be done with it? And it is focusing on a point. Then what should I do? I mean, will that radiation directly go and you'll use it directly with the to heat up the oil, or you'll do something else in between? Well, what has to happen, is that when it is being focused, on those, let's say a pipe, okay, I've got a pipe, okay, and from inside, let's say I'm going to pass hot oil or oil, which has to get heated up. Now, the radiation, that concentrated radiation is actually absorbed, right, by what it would be something like a black body. We know that a black body would absorb all the radiation. Okay, so effectively, what you need is some kind of a coating, which is very efficient for absorbing all the radiation. Okay, and this is known as a solar absorber. Okay. Now the problem is that any body, if I've got say it is absorbing the radiation, but it can also radiate heat, right, from that hot body. Correct or not?
Yes, sir.
Yes, sir.
Yeah. So, but if it re-radiates the heat, then, it's not going to be much use, right? So, what we have to do is that there are two very important things that we need to be able to optimize. One is that we have to maximize the absorption of the solar radiation which is falling, right? And so that is known as absorptance, all right, alpha, all right. And so you want a coating which will exhibit like 100% absorptance. All of it will be. You don't want it to reflect the radiation, okay? Because reflection means I'll lose, right? So I can't, for example, take an aluminium foil reflector. I mean, it will go and bounce back. It will get reflected from there, right? So I need something which will only absorb and not reflect the radiation, nor will it transmit the radiation. It will absorb. And I want it to be as high as possible. Okay. I also, now once it has got heated up, then what happens is that it's a hot body. Okay? And so it can emit infrared radiation. Okay. Because it's so hot. Right? Now, so what we want to do is to minimize the emitters, right? So you want a coating which will also have a low thermal emittance. Now the dilemma is that your emittance is actually uh, proportional to the fourth power of temperature. So the hotter I try to make it, it's like the I'm grappling with a very very serious problem, because hotter I'm trying to make it, T is large, and the radiation losses will be proportional to the fourth power. Okay, only thing is that it is proportional to this term emittance. Okay, so if the emittance term is low, then I can say that my total radiation, okay, re-radiation will be equal to emittance multiplied by T to the power 4, and the idea should be to try and make this as close to zero as possible, the thermal emittance, okay, and maximize the alpha. So effectively, a solar selective coating is one where I am trying to maximize alpha upon epsilon. Okay. And on top of that, it must be able to withstand that high temperature. It cannot degrade. Okay. It must not degrade, because if it degrades, then every now and then I'll have to replace the coating. All right. And in our country, the National Aeronautical Laboratory, okay, which is a CSIR lab in Bangalore, they had actually developed the best solar selective coatings in our country. Of course, what they did was not really for very high temperature applications, but many of these, you would have seen these solar energy based water geysers and things like that, where you're talking about temperatures of maybe 100, 150 degree, that kind of temperature, not more than that. And so they had made these excellent coatings, and they have also made coatings for very high temperature applications. Okay, but those are really not scaled up yet. So we are mostly dependent on imported these solar selective absorbers. Okay, has everybody understood the importance of the absorber, the solar selective absorber? High temperature. Is it clear?
Yes,
Okay.
sir.
And so that is what I'm trying to maximize. So all that solar radiation, I want it to get converted into a temperature rise, over here, right? And that's what you have to do. Now, let us try and see a little more, okay, on it. Now, one is, you see, I mean, during the daytime, uh, there's no problem. Like, for example, I can, as we said, we can pass oil, thermic oil, through it, and you can get temperatures of 400 degree, and you can run your, or higher, 800 degree, and you can run your turbine and generate power. Now the question is that what do you do at night time? Okay, and so this is a problem across the board. Okay, with all of these kinds of renewable energy sources which are intermittent, that is, they are not 24 by 7 kinds of energy sources. Okay, so one of the things that people are looking at is how do we uh, also store the energy. Okay, that means I generate a surplus amount during the day, and I store part of it, and then at night, I can basically run it on the portion that I have stored. Okay, so for storage, what people are looking at is you can see now, you can see that how the sun's radiation is falling. These are known as heliostat, where there's a large number, spread over God knows how much uh, square meter of area, and it's all focusing on this point. This is where you have got your solar selective coating, your receiver, okay, and this is what is heating up, okay. Now, and what you're doing is you have to pump some fluid, through this, okay, and that is what is then basically coming out heated up, okay, hot fluid. What people realize is that if you want to generate, temperatures of, let's say, 1,000 degrees centigrade, that even these organics, these oils, etc., none of these things will work. None of them can withstand those high temperatures. So, and air, you could have used air. Air is not bad, but the heat capacity of air is very limited. So, because at the end of it, it's not just temperature, it is the total amount of joules that I will get out of the system. That's what I have to look at. So what people found is that if you take molten salts, there are certain salt mixtures. Like if I take a mixture of sodium nitrate and potassium nitrate, now what happens is that these tend to form a eutectic, and so effectively what it does is that it lowers the melting temperature of the resultant composition. And so, so you can actually heat these things up and melt them without that much difficulty. Okay? You may be able to melt them comfortably at 600 to 800 degree centigrade temperature. Now, then what you do is that, so, and obviously, these are the important properties. One is that it must be molten. Okay? Otherwise, I can't circulate it. Second is that it cannot have an excessively high viscosity. So, you have to make sure that it's a system which is reasonably low in viscosity. Certainly, it has got to be pumping. And you have to imagine you're pumping things which are at a fairly high temperature. So the kinds of pumps, etc., those are all issues that you have to take off. Third, you see, if you are taking these kinds of salts, most salts are highly corrosive. So you need excellent material of construction, because otherwise it will corrode things up. And by the way, for these high temperatures, these towers can be very, very tall. Okay. And so you have got, you have to pump this liquid to a tremendous height, and then let it fall. Okay. So it's not easy, to meet all the requirements, including corrosion and viscosity. So there is intense research taking place in trying to make these kinds of eutectic compositions. Okay, and this is a open field. I mean, people might be able to come up with new compositions, and this is an area where you might find a lot of opportunity to do research. Okay, so keep this in mind that this could be a very nice area of research. Okay, and the others are that, as I told you, it must be molten, but it must not be volatile. Okay, so it must have an extremely low vapor pressure. It should not be volatile at all, because then it will go and coat on all kinds of things and make a mess, right? So you don't want any volatility of this eutectic. Okay, and the last, of course, which is as important as everything else, or if not more important, is the heat capacity. I mean, per kilogram of this molten liquid, how much heat can I store? Okay. I mean, otherwise, I have to pump huge amounts of liquid. I will require huge reservoirs. So I hope you understand how important heat capacity is. So these would be then the important things to note: corrosion, viscosity, ability to melt at a fairly low temperature, low vapor pressure, and very high heat capacity. Is that clear? Everybody has understood?
Yes, sir.
Okay. And then, you store this during the daytime you're generating this, put it in large reservoirs. Okay. And at night, I mean, it's at very high temperatures, 800 degrees, 600 degrees, whatever may be the type of heat I take. And now I have a steam generation over here. Okay. And I run my turbine. Okay. And generate power, and then this thing gets cold. Okay, and then I have a cold storage unit. Okay, and then the next day again I repeat the whole process. Okay, so I can have two units. All right, one unit could be to generate power during the daytime, and for that I can have a different solution. Okay, and for night, for storage, you could have this kind of salt eutectic, which you can use to store. Any questions around this?
So what is eutectic?
Ah, okay. Eutectic is basically, like many of these, even metals. Okay, when you put them together, there is a change in the property, of the composite material, right? And what it does is that it tends to lower the melting temperature. Okay, so
Yes,
it
sir.
will melt at a lower temperature than either of those solids.
Okay, sir.
Okay.
Yes, sir.
All right. Now, just to show you, this is, in fact, I thought I'll put it, it's fairly recent, 2019, and this is a company, there's a company which has been bought by Bill Gates, and you can see that these people are looking at energy in a very big way. Okay, and this particular thing is the same kind of thing that whatever I showed you, there is a concentration. Okay, now only thing is that here what I've shown you is just storage of thermal energy without any chemical reactions. Okay, I mean, I'm just storing thermal energy. Okay, and then I'm releasing the thermal energy. Okay, and running a turbine. Okay, but as such I'm not doing any chemistry. Okay, now you could, however, use these systems also to do chemistry. Chemistry in the sense that I can actually generate chemical fuels, and from this, and taking advantage of the heat. Okay, and because they can reach temperatures in this particular case of something like 1000 degrees centigrade, there are certain chemical reactions they are able to induce, and so finally then that also is a great solution, because I may finally want to just store them as chemicals, and those chemicals can be combusted, and you can generate your energy or whatever. But so I'm not just storing the heat as heat, but I'm storing it in the form of chemical energy, in the form of fuels. So if I'm generating certain fuels, later on, I can use those fuels and run a fuel cell. We'll talk about a fuel cell later on. Okay. And these things might be much easier to transport. These kinds of chemicals, if I make chemicals, I can even transport it from one place to another. There's no problem. Okay. Many times, what you can also do is that when these things, are used in a fuel cell, some of the constituents you can again recycle as reactants, into this reactor. So you can see it's a chemical reactor, means that there is chemical reactions that are taking place. Okay, so this is again another area that there's a lot of work going on, and for people in green technology, this would be of great interest. That how can you synthesize chemicals, important chemicals using solar energy? Okay, I'll of course discuss this in more detail either in next week's lecture or the week after. Now, so let us try and understand some of these chemicals, that people have been talking about, which are of great importance. Okay. Now, one of the holiest grails, okay, we say holy grail. Probably the one of the really much sought after holy grails is the decomposition of water to hydrogen and oxygen. Okay. Now, believe it or not, actually, if one could do it at the thermodynamic free energy of water, it's actually it's a very low energy demand, to be able to do it. Now, let me in fact try and show you. So this is, let's say, if I take 1 mole of water, and I'm splitting it to H2 plus half O2. Okay, it requires 1.23 electron volts. Okay, thermodynamically, and 1 electron volt is equal to 1.6 into 10 to the power minus 19 joules. So this comes to 1.97 into 10 to the power minus 19 joule. Now this is per molecule. Okay. So if I have to do it in terms of mole, so I have to multiply this by the Avogadro number. Okay, 6.023 into 10 to the power 23. Okay, and this is the value you will get. So if I were to generate 1 mole of oxygen, okay, so it will be double. So I'll take 2 molecules of water. It will give me 2 moles of H2 plus 1 mole of O2. Okay, so it will be double this value. Okay,
Right.
so that will be 237 kilojoule per mole.
Yes.
Okay.
Yes.
Huh? Is that clear?
Yes.
And 237 kilojoule per mole, I mean, it's not such a big figure, right? If you divide that by, if you express in calorie, what? It will be about 50 some kilocalorie per mole of oxygen. Okay, so not a huge amount of energy is required if you can do it in a smart way. Okay. Now,
Sir,
what is the way in which you are already familiar with, where you can actually decompose water into hydrogen and oxygen? Is there any method that you know?
Sir, I think it's Fischer-Tropsch process or shift water gas shift reaction, I guess.
No. That is, yeah, but that is, you are reacting it with CO,
Yes.
Okay, in water gas shift reaction.
Yes.
You are talking about CO plus H2O going to CO2 plus H2.
Yes, sir.
No, you
Yes.
don't simultaneously get H2 and O2 from water.
Yes.
You understood? Huh?
Yes.
So what is it? Oh,
Electrolysis.
Any method that you know for converting water into hydrogen and oxygen?
Electrolysis.
Absolutely. Electrolysis. Now we will talk about this later on. We'll talk a bit more about electrolysis. Uh, but just look at the fun. If if you try to, you know, let's say just heat up water, okay, or let's say if I say, yeah, and I let's say I even heat it up to um, or say about 100 degrees centigrade, or that or even ambient temperature. Only one molecule in 100 trillion, right, would be dissociated by the effect of heat. So it's a very tiny fraction. Now, if you are heating water, I'm talking about just heating water to 2200 degrees centigrade, 2200 degrees centigrade. Even then, only 3% of the water will break up into things like hydrogen, oxygen, etc. Okay, at 3000 degrees centigrade, 3000, it will be about half the water molecules will get decomposed. So, what does that tell you actually? Why is that happening? Why do you need such high temperatures? When in fact the thermodynamic energy requirement is quite modest. Activation energy. You're familiar with activation energy?
Yes,
Yes,
sir.
sir.
Yeah. So, I mean, always, look at these things. Like, for example, if I've got H2O and I cannot generate half O2, I can write H2O going to H2 plus half O2. But half O2, there is no half O2. You can only make one oxygen molecule. So it is like 2H2O will become 2H2 plus O2. What is the oxidation state of oxygen in water? What is it in carbon dioxide?
So -2
Sir, it's plus
oxygen.
2 in water.
Huh?
Plus 2
Huh?
in water.
-2, you said. -2 you're talking about in water, right?
Yes, sir. -2 in water.
Yes, sir.
Absolutely. Correct. Right? So, and how much is it in O2? O2 molecule? What is the oxidation state? How much?
0.
Yeah. Why are you so nervous? You know the answer. Don't be so scared. I think you're like too inhibited and you're thinking always, I'll give the wrong answer. Don't worry. Okay. So you can imagine that to make one oxygen molecule, I really have to effectively bring about a 4-electron transfer process. Is that clear? One O is 2 minus. So 2 of the water molecules means 2 into 2 minus, that is 4 minus. And from 4 minus, I have to go to 0 state. That means I have to have a 4-electron transfer process. Okay. Now, whenever you have to have these kinds of multiple electron transfer processes, they're not easy. Okay. They're very difficult to do. So, for example, now imagine, like if I break up water and say I want to make it into H and OH. Okay. Now, both are radicals and extremely energetic, very high in energy, H and OH. And once I make H, I can of course combine two H's and it will form H2. You know? But it requires a huge amount of energy, to split it like that. Okay? And that's why what you require is some kind of clever way, catalytic ways of being able to do the same thing at a lower temperature. Okay? Is that clear to everyone? Have you understood?
Yes,
Yes,
sir.
sir.
Okay.
Yes, sir.
So let us now look at, some of these extremely clever ways, that people have tried to solve the problem. Okay. And I will go through a few of those. And it's very interesting. This is another thing that you should always remember, that in all of the cases, everybody's goal is to basically convert water into hydrogen and oxygen, H2 and O2. And you have already talked about electrolysis. That's one way. Okay. Let us see what are the other ways that people have looked at, to do the same thing. Okay. So this probably is the first one, and it is known as the SI cycle. Okay. It was invented in the 70s by this company, very famous company called General Atomics. Okay. And so let us try and understand what they did and how smart they were. Okay. So what they're doing is that, and another thing which you must remember, when we do electrolysis of water, uh, do you get the hydrogen and oxygen separately, or are they all mixed up? If I do electrolysis, will I collect them separately or in a mixed state?
Probably it will be mixed state.
Mixed state? No, it won't be, because you see, I'm generating it at the anode and the cathode, right?
Yes, sir.
In the cathode, I'm generating hydrogen, and at the anode, I'm generating oxygen. So I can draw them off separately. Okay, and
Okay.
that's what makes it a very nice process, because if they were all generated in a mixed state, firstly, it would be highly explosive. The hydrogen and oxygen can combine again and explode. And secondly, if I have to separate it out, there would again be an elaborate process of separation, right?
Yes, sir.
Okay.
Yes, sir.
Yeah, and so when I can actually, in fact, these were experiments that we used to do in school. You can show the oxygen and hydrogen being collected in a burette or something separately. Okay, so in these processes that I will now show you, they also have this advantage that you collect the hydrogen and oxygen separately. Now let's see what they actually do. Okay. Now, this is one process. It's actually based on, firstly, a very interesting phenomenon which is quite well known. All of you are familiar with the contact process?
Used to make H2SO4.
Yes, you know. Okay. Yes. Okay. So, contact process is about taking sulfur dioxide, SO2, and it is oxidized to SO3, and then SO3 dissolves in water or in sulfuric acid, and that's how you generate sulfuric acid. Okay. So now what is very interesting is that when you look at the phase diagram, phase diagram means the chemical equilibrium diagram of, you can't see it properly here. Maybe I'll just try to blow it up once. Yeah. Okay. So if let's say I take a mixture of SO2 and O2, such that, I can, if I react it fully, I'll get SO3, you know. Now, what happens is that at different temperatures, you will see different behavior. Like if the temperature is below 700 Kelvin, it will want to remain as SO3. Okay? But if I increase the temperature, then for some time I'll get both SO3 and SO2 being co-present, and if the temperature is very high, then there will be no SO3 formation and it will be only SO2. Okay, so what these people have done is, and the reverse is known, that if I take sulfuric acid and if I, like, let's say, spray it in an oven, okay, at a very high temperature, something like 800 degrees centigrade, it will decompose to form SO2 and O2 plus water, right? So because taking, basically taking advantage of this particular chemical equilibrium, okay? Now, so there is a way in which you can decompose sulfuric acid to make sulfur dioxide and oxygen. Just make a note of it. Now, there is also and this reaction is endothermic, requires energy. Okay? Now, there is also a reaction where I can react iodine, I2, with sulfur dioxide, and it will form HI and H2SO4. Okay, so I get HI and H2SO4, and remember this SO2 will basically come from here. Okay, now, and then what have I formed here? I've formed HI. Now, and this reaction is exothermic. There is a third reaction which is known, that if I heat up HI, it decomposes to I2 plus H2. Okay? So you can see in one reaction, I am generating oxygen. In another reaction, I am generating hydrogen. Okay. Now, if you balance out all these equations, right, what you, and just add them, right? So you can see, like for example, here I'm getting 2 SO2, okay? So I over here I am getting 1 SO2. So I have to multiply this by 2. So I'll write 2I2 plus 2 SO2 plus 4 H2O, giving you 4 HI plus 2 H2SO4. Okay, and then so I've got this, okay, and then similarly, I can, because I'm getting 4 HI here, so I can multiply this by 2, so I'll get 4 HI, okay, going to 2I2 plus 2H2. And what happened over here, because I had 2I2, because I had 2 SO2s, so everything will cancel out, okay, from the left hand side and the right hand side, and the only thing that will remain is I can write it as 2H2O going to 2H2 plus O. Have you understood the reactions?
Yes, sir.
Okay, all right. So I can also show it schematically here. Like, let's say, what are we saying? In this first reaction, reaction 1, I've got iodine, and then SO2 is coming in, okay, and I've got water. Okay? So actually, if I have to multiply both by 2I2 and 2SO2, and I'll put 2H2O, okay, and effectively, what will I form from that? I am forming, effectively, from this reaction, I am forming HI and sulfuric acid. Okay, so I'm just doing a separation here. and I'm taking out the H2SO4 and I'm taking out the HI. Okay, and this HI then I am putting into the third step, and from which I'm getting H2 and I'm getting back my I2 for my reaction. And this H2SO4 I heat it up and it gives me oxygen which is coming out, and it gives me SO2 which I'm feeding back here, right? So everything is beautifully cycled, and the only thing is that I've got hydrogen and oxygen coming out. My input is H2O and my output is H2 and O2. Okay, now why did I do all this? The reason is because whereas over here, even with a temperature of 3000 degrees centigrade, I could only convert half the water molecules into oxygen and hydrogen. Here, I can do that same thing at a temperature of 830 degrees centigrade. You understood? Okay. And 830 degrees centigrade is a temperature that I might be able to achieve through solar concentration. Whatever we discussed, those parabolic dishes and troughs and stuff like that. So, in other words, both of these endothermic reactions I can satisfy by solar energy in principle. Okay, and the exothermic reaction is my heat sink. Okay, and these are my ones where I need a heat source, and that heat source can be solar energy. Okay, so let us see what it says. The sulfur and iodine compounds are recovered and reused, hence the consideration of the process as a cycle, and that is why it is called the SI cycle, sulfur iodine cycle. This SI process is a chemical heat engine. Heat enters the cycle in high temperature endothermic chemical reactions 2 and 3, and heat exits the cycle in the low temperature exothermic reaction 1. The difference between the heat entering and leaving the cycle, okay, is basically the resultant amount of heat that I stored in the form of chemical energy, that is H2O going uphill to H2 plus O2. That's the difference in heat. Okay, now look at the beauty. Where all did we see this heat input, heat sink, heat source? We saw it over here. Heat gets in, heat comes out. So there is, depending on, you're doing more or less the same thing in every case. You are taking advantage of high temperature solar energy. Okay, but in every case, and here you are getting power, again you are heating it up. Okay? But the end way and the end thing that happens is so different in these processes. Okay, and but let us look at, there are there are so many things. It looks easy. Can someone tell me just quickly in 5 seconds if you have spotted anything that looks to be a problem? Anything that occurred to you? Well, see, everywhere it is saying the HI is then separated by distillation or liquid-liquid separation. The water, SO2 and residual H2SO4 must be separated from the oxygen. That's not so easy to do. All of these things are the complexities. So while it looks great on paper and you can draw this scheme, but you have to ask, hey, how am I going to do these separations? Okay, so always in renewable energy, this course, you'll find that if you look at it in a very naive way, everything will look nice and rosy. You start being critical and say there is something definitely not good about it, and surely you'll find it. Everywhere there is something which is not good about it. Okay, now so the advantages and disadvantages, okay, one is that all are fluids, they are all gases or liquids, so it's very easy to transfer from one place to another. Okay, and that's a huge, whereas if you have to filter a solid, it would be a mess. Okay? So that's a huge advantage. Apparently, the heat utilization efficiency is about 50%. And he calls it high temperature. 850 degrees centigrade, of course, is a high temperature, but much less than those 2000, 3000 degrees centigrade temperatures that we talked about. And it is achievable. It is not beyond solar energy to achieve these. Okay, completely closed system. Okay, without byproducts or effluents. Beautiful. I only need an input of water. I get oxygen and hydrogen coming out. Everything else is recycled. Okay. Now, disadvantage, corrosive reagents. Okay. So you need advanced materials for fabrication of these reactors. It would be very well suited to solar, nuclear energy. I mean, even in nuclear energy, we generate these kinds of very high temperatures now. So one could easily carry out this SI cycle. And even though, there are lacuna such as this separation, etc., which are actually not so easy. And we'll see a subsequent cycle where it's been solved, but by and large, out of all the cycles, this one is the most developed. And in many ways, I will say the most practical. Okay. So now you have seen a different way of making hydrogen and oxygen, which is not by electrolysis. One more disadvantage, which is not mentioned here, but I think I'll write it down, is, you can imagine thermal cycling, okay, that they are all at different temperatures. So if, for example, you are generating at 830, you'll have to again probably cool this thing down. So again, there's going to be a lot of involvement of heating, cooling, heat exchange, so other big problems. I'll just put another problem. Right? Agreed? Okay. Now, so we know what are the drawbacks, and we said that separation, for example, was a big drawback, in this particular scheme. Now, let us look at another scheme, two more schemes, okay? And now, it's in a way almost like utopia, but very, very difficult in practice. But what it is that, it takes advantage of this particular compound, like for example, cerium 4, 2C4, C4O2, that is this one. Okay. Now, what has been found is that two molecules of this, right, if you heat it up to 2000 degrees centigrade, so it's an improvement over the 3000 degrees centigrade, but 2000 degrees centigrade, while one has written concentrated sunlight, it's not a matter of joke to reach a temperature of 2000 degrees centigrade. Easier said than done. Okay? But anyway, schematically, okay, when you do that, what happens is over here, of course, the oxygen is in the O2 minus state. So that's how it becomes C plus 4, and two of these oxygens, O2 minus, O2 minus. So that is the overall neutral compound, C4O2. Okay. And when you heat this, oxygen comes out, that is oxygen 0. So it's releasing 2 electrons from these oxygens. So each of those electrons, is going and reducing each of these cerium 4, and so it becomes cerium 3. So it becomes cerium 3 2 and O3. Okay, so that's effectively what you're doing, right, over here. And one oxygen came out. Okay? Actually, one oxygen means half an oxygen came out, not one. And put half. Sorry. Yeah. Okay. Now, then what happens is, and that happens at a fairly low temperature. Okay, you add water to this compound, heat it up to 400 degrees centigrade, and hydrogen comes out, and you get back this compound. So you are recycling the whole thing. Nothing is lost. Okay, and what happened finally? I got H2 and half O2. Okay, that's what happened. And now, as I said, except for the fact, that this particular reaction requires 2000 degrees centigrade temperature, it's a beautiful scheme. Conceptually, it's a great scheme. All right. Now, this is another scheme where the temperature requirement has been brought down to 500 degrees centigrade. Okay. And there are certain similarities between the two. Now, here, what you're doing is that you are first taking this compound, Cu2OCl2, two of them, just like here, 2 molecules. Okay. And what's happening is that this at 500 degrees centigrade decomposes to 2CuCl and oxygen gets released. Okay, so 2 and O, so that will be O2. Okay, and then you have got 2Cu and 2Cl, which will form 2CuCl. So the oxidation state of copper over here, right, is basically not the same. This is copper 2. This is copper plus 2, right? And here it is copper plus 1. Why? Because O2 minus oxidation state went to O0 in O2, and those two electrons basically reduce the copper to copper chloride, CuCl. All right. Now what they're doing is that it's interesting in a way. Now, in this particular reaction, when they got this oxygen, what they're doing is that they are doing an electrolysis of this CuCl, right? And in the process, effectively what is happening is when they're doing the electrolysis, they're converting, copper CuCl back into CuCl2, okay? And at the cathode, H plus is becoming H2. Okay, so that's how they're getting their hydrogen. Now, and the hydrogen is coming from HCl, the H plus is becoming H2, and the Cl is combining with the Cl, and that's how it's forming copper chloride. Where did the HCl come from? I missed out one step, that CuCl2, this stuff, is in the presence of water, okay, at a fairly low temperature, it is reacting to form 2HCl, this one, and this compound. Okay, so you can start from here. It's reacting with water, forming HCl and this compound. This compound is being heated to liberate O2 and form CuCl. Then this CuCl and HCl is undergoing electrolysis to get back CuCl2 and to get H2 gas. The advantage is that now you are able to use a relatively more available concentrated sunlight, which can, reaching a temperature of 500 degrees centigrade is not a problem, so you can do that. But the question that you have to ask yourself is this really making any sense? Suppose I say it's not making sense to me. Why is that? Can one of you give your own reasons as to why you don't think it's such a great scheme, even though I can do it at 500 degrees centigrade? Well, the reason is, you yourself have told me that I can electrolyze water to hydrogen and oxygen. Why I will go through all this jhanjat and then later on again have another step for electrolysis? It doesn't make sense. I would much rather than do the direct electrolysis. Maybe, we'll have to see what happens to the energy and things like that, but conceptually, this does not look so great. Because I have to do too many things, and including an electrolysis, I can just straight away do electrolysis of water and forget about all this. Okay, so it's important that when you are looking at these things, you also critically ask yourself some questions. You say, hey, is it really so great? I don't see anything so great about it. Okay? All right. Now there is another. You see, all of these schemes, whether it's the SI or the scheme, we talked about that. These compounds will have to undergo heating, cooling. So 2000 degrees centigrade, from there I have to bring down the temperature to 400 degrees centigrade. Can you imagine how much of heating, cooling, heat exchange is involved? Even here, although it's not much, but still, some amount of heating, cooling is involved. So people have been trying to see that is there any system, where you might be able to do it under a isothermal condition. That is, you don't change the temperature, okay, in this process. And they then came up with this scheme. It's called the Hercinite scheme. Hercinite cycle is basically a reaction of ferrite. This is known as ferrite, the structure, okay, with alumina. So ferrite and alumina in presence of heat are reacting, okay, and what are they forming? It is basically, undergoing a change, okay, and there's a cross reaction. It forms CoAl2O4, okay, plus FeAl2O4, and it liberates half a molecule of oxygen, okay, and we will discuss the temperature. After that, very interestingly, this stuff, if you contact it again with water, then what happens is that it reconverts to this compound and it releases hydrogen. Okay, this is the H2. So ultimately, what did I do? Just like the previous cases, I am recycling all my these compounds, and finally my input was, one is H2 over here, okay, and my output is H2 plus half O2. So again I have done water splitting, okay, and this time I have done it under isothermal conditions. Now it is fine, and you can see, like, this is an isothermal condition, okay, 1400 degrees centigrade, they are doing this first scheme, The second scheme also doing at 1400 degrees centigrade. But there is, in other words, there is no thermal swing. The temperature is remaining constant. But it is not so simple, because I have now a pressure swing. Why? Because after I have completed this reaction, firstly I have to make sure that all my oxygen has been removed, and then I have to introduce water, okay, for my hydrogen production. So it is not as if there is no complexity. It is not so easy, to remove the oxygen, to put the water, to make sure that it doesn't in any way mix together. So there are issues that you have to look at. And the moment I've got a pressure swing, or I'm trying to make sure that all my oxygen has got released, there will be complexities in recovering that oxygen subsequently. All right. So those would be the issues. But I can tell you that this is considered to be a very, very important scheme. And just to show you the importance of water, in the second cycle, that is this part, when they're putting water, that depending on how much water you are putting in, okay, so you're pressurizing the system. It is not under ambient pressure. So you have to put water in, and so that's the pressure swing. Okay. So depending on, if you were to put in water, means steam, at a high pressure, then you get a very good conversion. But if the pressure of the water, of the steam is inadequate, then your conversions are very poor. Okay. So here the complexity is removing oxygen, putting water under pressure. Okay. So that versus this so-called isothermal process. Okay. Is that clear to everyone? Everybody understood the Hercynides cycle?
Yes, sir.
Okay.
Yes, sir.
And understood the copper and the cerium cycles also? You understood all the
Yes, sir.
cycles?
Yes, sir.
Okay. Now, let me tell you that people have not only been focusing on, one is of course, and this is the holy grail, how to split water into hydrogen and oxygen. I don't know if you know, if you're reading the papers, but even India has committed itself to a hydrogen economy. And so we are talking about, requirement for large amounts of hydrogen. Okay. And I will show you, of course, what is the current status and things like that. But obviously a huge amount of work will be required to come up with practical solutions. Okay. I mean, we might be committed to all these, but making it practical is not so easy. Now, there are also other very interesting things that people are looking at. The detailed schemes you won't be able to see, it's too small, okay? But the broad equations you'll be able to see. Now, one is that you should know, there is a lot of work going on in the area of ammonia. One is, of course, we have seen ammonia for refrigeration. That's a separate application of ammonia. Okay, but people are also trying to see, whether they can devise some schemes, for solar energy storage, and all of this is related to storage. Okay, now let me ask you the question. In the Haber process, hydrogen plus nitrogen going to ammonia, uh, what do you think? Is it an exothermic process or an endothermic process?
Exo, sir.
Wonderful. Exothermic. Okay. Now, so obviously the reverse process is endothermic. The decomposition of ammonia to nitrogen and hydrogen. Now, so what you can do, and this is a scheme. Now, these are being looked at by this company, Pacific Northwest, is one of the leading labs in the US. It's a government lab, okay, and they are doing extensive work, where what they're doing is that they're trying to use solar energy, okay, at very high temperatures, which you can get. You can decompose ammonia to nitrogen and hydrogen, okay, and so that is why they have called it on sun. On sun means this will happen when there is sun. And so, and when I say sun, I'm talking about concentrated solar energy. Okay. Now, after that, what happens is, for those who are familiar with the Haber process, actually the reaction between hydrogen and nitrogen to form ammonia today is one of the simplest reactions. The complexity of the Haber-Bosch reaction is really to make pure hydrogen and pure nitrogen. Once you have made pure hydrogen and nitrogen in 3:1 ratio, after that making ammonia is very, very simple. Okay. Today, in fact, it is not an issue. Now, when I'm doing the thermal decomposition, I'm not introducing anything else. It's forming H2 and N2. So I don't have any purification related problems. I just then have to do the reverse, the Haber process, and reconvert it into ammonia from nitrogen and hydrogen. Okay. And that could be off sun. Off sun means I don't need the sun. It's an exothermic process. It will occur on its own. It will liberate heat. In fact, what we are trying to do is really the energy that you have stored, in decomposing ammonia to nitrogen and hydrogen, you are basically getting that back when you are recombining to form ammonia. Okay, so that is a wonderful scheme, and this kind of thing is again being actively looked at. And I would say these are the kinds of things, all the things that I'm telling you fit in very well with green chemistry, with green technology, the area that you are in. Okay, so have a look at it. Similarly, there is another one. Okay, I won't go through all the schemes, but I'll show you this, where people are looking at, for example, I can take methane, okay, and methane, again, when we say you can, with the, this is what we call as steam reforming, okay, where you take methane plus water and you form carbon monoxide plus hydrogen, right? Now, this requires a lot of energy. Normally when you do steam reforming, it's not an issue because part of the methane you are combusting, and you are generating the energy to carry out the steam reforming of the rest of the methane. So part of the methane is just becoming CO2 and part of it is getting converted into CO plus 3H2, okay, by this process. Now, suppose I did not want to burn methane, then because there's no point. If I have to do that, then why would I do the cycle? Okay? So I can generate the heat that is required to carry out this reaction. Okay, I can do it using solar energy, concentrated solar energy. Okay, and the reverse reaction, which is that syngas, CO plus 3H2, reforming methane and H2O is thermodynamically spontaneous, so it releases heat. Okay? So I can get back that heat, so this also can be a wonderful storage system. Ammonia going to N2 plus H2 and methane going to CO plus H2. Okay, so I won't go through the other schemes, but I want you to have a look at it. There is another scheme which has been made, with methanol, but let's just focus on these two schemes. Okay, now the assignment, you don't have to submit it, but I want you to do it at home, is that, I'm telling you in a very qualitative way, this is going here, that. What I want you to do is that I want you to find out the thermodynamic and kinetic parameters for these reactions. What is the thermodynamics and kinetics of ammonia decomposition to H2 and N2, and likewise for methane going to syngas, and what is the thermodynamics and kinetics for the reverse reaction, which is the spontaneous off-sun reactions. Okay, so otherwise, I think these schemes are great, and I can tell you that these are the areas where huge amount of work is going on in the area of renewable energy storage, because people have realized, that battery is not the only way to store energy, that there are many other ways. So I have been telling you one after the other, all the different ways, starting from eutectics, salt eutectics, to various things which basically help to store energy, okay, solar energy. So this scheme over here that we discussed is basically the scheme, all right, which is really being used to produce hydrogen in the world today, right? It is steam reforming. All the people who produce hydrogen, you go and ask them where your hydrogen is coming from, they will tell you steam reforming. Okay, so steam reforming is basically you take any hydrocarbon, in the simplest, whatever we discussed is methane, natural gas, right? And so that's what you're doing. That's the previous reaction which I showed you, this one. Okay, so you're taking this plus water, it's getting converted into hydrogen plus CO plus carbon dioxide. And then of course there would be some unreacted methane and some small amount of water, etc., which will also form. Okay, and this is the reaction which is carried out the world over with a nickel catalyst, okay, at about 10 to 25 bar pressure and 800 to 900 degrees centigrade temperature. Now, there is no question that this is wonderful. The best way of making hydrogen. Only thing is that don't forget that these are all fossil fuels. Whether it is natural gas or crude oil, this is all fossil fuel. And the world is running out of fossil fuel, world is running out of natural gas. There's a serious problem world over, and climate change. Okay, so doesn't matter how great it is. Fact of the matter is that it would be ridiculous to keep comparing with this. It's good to compare as a benchmark, but I know that this is not what I'm going to do 50 years from now. There will be no natural gas or crude oil. It will be gone. Okay, but why it is important is that you can actually figure out that what exactly is the kind of energy requirement, in these kinds of processes. Okay, and if I do, let's say, hydrogen production by some other process, then how will it compare? Is it 10 times as costly, 5 times as costly, 2 times as costly? How costly is costly? We need to know. Okay? Now, I am not going to go through the details of the process here, but what is most important for you to know is that this is what is known as the reformer, the catalytic reformer. This is one what has that nickel catalyst, okay, and this is the one into which my fuel, okay, you can see fuel is going here and fuel is coming here, and water, water will go in over here at some point, okay, and and that's what is producing your hydrogen and in this catalytic reforming process, okay. Now that thing, uh, the actual details are much more elaborate, okay. So I'm not going to go through the whole steam reforming process because that's really not part of your course, but what you need to understand is that these catalysts can get poisoned by the presence of sulfur, which is invariably present in natural gas or crude oil, so you need a desulfurization, okay. And then when I get this product, coming out, I have to take out the hydrogen from all of this. And that is done with the help of adsorbents. There are different kinds of adsorbents, okay, which can remove carbon monoxide, carbon dioxide, methane, okay, and finally out of that, so that I can get hydrogen of high purity, okay, coming out. That is the hydrogen which world over people are using, okay, made by steam reforming. Okay, now similarly, people are also looking at making hydrogen from methanol, okay, and methanol has the advantage, that because methanol is a liquid, it's easy to transport. Okay? So that's one advantage, that people can produce hydrogen locally by taking methanol. But today, if you ask, where is all this methanol coming from? All methanol is coming from effectively natural gas or crude oil, because it is first converted into syngas, and syngas is converted into methanol. Okay, and the reverse basically is being done with the help of this copper zinc catalyst, which cracks the methanol and converts it into these. Okay, so it's all great, but both of these are fundamentally based on natural gas, unless, okay, like for example over here, one of you could have asked me the question. You could have said, why? I will generate biogas. After all, what is biogas? It's CH4. It's like methane. It's like natural gas. Now, if you believe that you can generate such large quantities of biogas to meet the world's requirement for hydrogen, wonderful. But today it doesn't look to be the case. Okay, but if you could do it, if you could find some brilliant solution, then I mean, you would have solved a huge problem, because then we would just continue to do steam reforming. The only difference will be that instead of taking natural gas or crude oil, I will take biogas and do it. Okay, so it's not irrelevant. We will say, let's put it down, because otherwise I'll forget and you all will also forget. Steam reforming can be extremely relevant. Can continue to be extremely relevant if natural gas or crude oil can be substituted with biogas. Wow, then there is no issue. While I was talking to you, I suddenly thought, why not? If we can do it.
So you talked about the replacing the methane with biogas, sir.
Yeah.
I recently read a paper regarding that, sir.
Okay.
It stated production of green hydrogen through, there's all this fuss going on regarding blue, green, turquoise, and gray hydrogen, sir.
Yeah.
So they mentioned making green hydrogen through biogas via chemical looping, sir. So how is it exactly green, sir? Again, producing CO2 from it, sir. So
No, no. But the point is, you see that the biogas came from a bioresource,
it's a renewable
right?
resource, sir.
Huh.
Renewable resource.
And that bioresource came from what? It came from fixing of carbon dioxide, right?
Yes, sir.
So in a way, I have a, I mean, your cycle, what you are doing, what they are doing, of course, I'll be generating CO2. But if I am producing the same amount of CO2 as which it is consuming to form biomass from which I am getting biogas, then it would be great, right?
Yes, sir.
Okay. So only then would it be green, not otherwise.
Okay, sir.
Okay. Now, the point is that the next biggest competitor, the stuff that I showed you, these cycles are still in the realm of pilot plant research and things like that. Nobody can say any commercial units, okay, have come up based on any of this. And I never find people talking about what is the energy balance in all of this. In fact, you would find this kind of a unit, if you go next to our workshop, general engineering, there used to be a lab there, where they were working on this cycle. Okay, but it's closed now, the project, I think. Uh, but the truth is that the only thing that is the most realistic competitor to steam reforming is electrolysis, the good old electrolysis that you have learnt about in school. Okay, that is still the greatest. It's the best way to do things. Okay, now before we come to electrolysis, and why is there so much talk about hydrogen? Because for example, if I take the fuel cell, okay, what is a fuel cell? A fuel cell is one where, like, let's say if I take pump hydrogen and oxygen, and I can convert it into water and generate the power. Okay, that is a fuel cell where my hydrogen is a fuel, but I'm not combusting it. I'm not doing it by burning H2 and O2 to make water. I'm indirectly doing it by generating power in the process. Okay, that's what a fuel cell is. Okay? I can do exactly the same thing with methanol. In fact, I remember long time back, 2005 or I think 4, Mercedes-Benz had presented me a fuel cell which was running on methanol. It was, of course, to run a toy car, a toy Mercedes, but still, it was beautiful. You just put in a few drops of methanol every now and then, and your car is running. Okay, it is a toy, but still, I realized the power of fuel cell. Okay, and so what are we doing in a fuel cell? In a fuel cell, we are trying to do the reverse. That is, I have got my fuel and now I need to extract energy from it. I need to extract power from it. Okay, so I do that with the help of a fuel cell. So, for example, I take methanol, and this is the reaction. So this is my anode. Okay, this is my anode. Okay, this is my cathode. Okay? And this is a membrane. We'll talk about the membrane. Okay? What is the reaction? Methanol plus 6OH minus gets converted into CO2 plus 5H2O plus 6 electrons. Those electrons are flowing in the external circuit, okay, to the cathode. What's happening at the cathode? At the cathode, I'm pumping oxygen. Okay, so that oxygen plus, and I'm putting in water, oxygen plus water plus those 6 electrons which came from the anode, okay, it will form 6 hydroxyl ions. Okay? Now, this membrane is an anion exchange membrane. So it only allows anions to pass through. Okay? So what it does is that the OH minus that forms here, it passes through this membrane into my anode compartment, and that OH minus is what I am requiring for this reaction. So ultimately what happened? Ultimately I just converted methanol into carbon dioxide, okay, and water. That's all. Okay, that's all I did. And I can do exactly similar thing with hydrogen and oxygen. I pump hydrogen in one direction, okay, and it will, in presence of hydroxyl ion, it will form water and it will release electrons which will go to the cathode. My reaction here will be identical, and again I'll generate hydroxyl ions, okay. Those will migrate towards my anode, and I will basically provide the hydroxyl which I need for this reaction. And so ultimately I've just converted hydrogen and oxygen into water. That's what I've done, okay. And these are the catalysts, platinum, ruthenium at the anode, and maybe at the cathode I'll use a nickel catalyst or something like that, or maybe a carbon electrode, okay. And mind you, this is what gave rise to the, once these fuel cells and all had been created, the space missions, etc. were taking place with this. This is what was being done. That's how the spacecrafts were generating their power. Okay, and this electrode and all these electrodes were developed by great companies like DuPont. And once people realized that it's a very, very nice way, why should I just burn this and make CO2? I can just get power out of it. That's what a fuel cell is. Okay. Now, I am not going to go through the energetics of water electrolysis. Okay. But what I want you to do is that maybe I'll pass on an article also to you, that you can look at all the details, the cell reactions, the relationship between free energy of reaction and the cell potential. I think you all already know delta G is equal to minus NFE. Okay. And, if, for example, I do the same thing, not at constant pressure, but I do it at constant volume, and I vary the pressure, then instead of delta G, I have to put in the Helmholtz free energy term. So that is delta A. That's the only difference. Otherwise, the two are basically the same thing. Okay. And from all the data on the standard reaction enthalpy, the delta N for the reaction, the entropy, delta S values, etc. You can actually calculate, okay, that the cell potential would be about 1.21 volt. This is what we talked about. This is what you would get back, if you operated a fuel cell with hydrogen and oxygen. Okay? Now, the reverse is electrolysis, where you are trying to make hydrogen and oxygen. Where is the question of making a fuel cell and getting water from hydrogen and oxygen unless I have hydrogen and oxygen? Okay, and steam reforming is fine. Okay, but that's not necessarily the way in which you will get hydrogen in the future. But let us not worry right now about what will be the source of my energy to drive my electrolysis. Let us just look at electrolysis of water. One is, of course, what you have learned in school. Okay, or I can take water, I put in some sodium chloride, make the solution conducting, put two electrodes, and carry out electrolysis, I'll get hydrogen and oxygen. Of course, when we are doing those experiments, we are not bothered about how much power we are putting in, what is the energy balance, etc. If we really have to start looking at all that, then the situation would be different. Now, let me tell you how commercially, right, how electrolysis is carried out. Okay? It is carried out, the most popular is under alkaline electrolysis conditions. Okay? Yeah. So, under alkaline electrolysis conditions, what you do is you actually make the anode compartment alkaline. Okay? Why? Because this oxidation of OH minus, to oxygen is most favored under alkaline conditions. Okay, so I do that. So you can see I am oxidizing hydroxyl ion, my alkaline thing. I am generating oxygen. Okay, and what else am I getting? I'm just getting water. Okay, so you can see two of this OH minus, so it will form H2O plus half O2. So that's the H2O. Okay. Now, in the cathode, what am I doing now? In this particular case, I am just basically reducing water. Okay, I am reducing water effectively to hydrogen. Okay, and it's a reduction, so it picks up those two electrons from here, and I form hydrogen. Okay, and what am I left with? I am left with hydroxyl ion, and that hydroxyl ion basically migrates to my anode, and so once I put in my alkali is not getting consumed. It is basically being consumed and also getting generated. Okay, and so it's just that I need an initial alkaline condition, but my alkali is not getting consumed. The only thing that is getting consumed is really water. This water, one water here and one water here. So if you take the difference of these two, this water is being produced, this water is being consumed. If I take the difference is one water, and what I got out of one water, I got H2 and I got half O2. That's what I got. Okay, now there are other very important things which people have found out, that if you do this alkaline electrolysis of water at high temperature, something like maybe at about, you can see 150 degrees centigrade. Okay, at 150 centigrade means under pressure, this electrolysis is being carried out, and they found that the efficiency of electrolysis is far superior. Second, the very interesting thing is that because I'm doing it at high temperature, I also have to apply a high pressure to maintain the temperature. Otherwise, the water will evaporate, right? Now, so I am generating hydrogen and oxygen under pressure. In other words, it is like as if I am taking an empty cylinder and filling it up with hydrogen and another cylinder with oxygen. Okay, so the cost of pressurizing the cylinder, is reduced. Even if I have to subsequently pressurize it to much higher pressures, like 200 bar or whatever, at least my initial pressurization has been done during the electrolysis pressure process itself. Okay, so this is electrolysis under pressure. Now, because I am doing the electrolysis under pressure, okay, I obviously will also need some amount of additional power, and so the requirement over here, you can see, is not 1.2 volts like we had seen. It's closer to about 1.48 volts. Okay, but even so, it's magnificent, and the efficiency. Oh, there is one more thing which you need to understand, which is important, which is that what are at the end, what will I be judged by? I will be judged by how much current did I pass, and what fraction of that current was actually used in converting to oxygen and hydrogen. And that percentage is 80%. The other very important thing that I'll be judged by is, how much oxygen and hydrogen can I produce from a certain cell? And that will depend on the current density. How much current am I flowing per unit area of the electrode? Because my electrodes are costly, my cell is costly. So the higher I can make my current density, the better it is. My capital cost will go down. From the same unit, I'll generate a lot more hydrogen and oxygen. And today, you can operate these things at a current density of 10 kiloampere per meter squared. So if you see 10 kiloampere means 10,000 ampere, and meter squared is 100 centimeter into 100 centimeter, which is 10,000 centimeter squared. So it becomes 1 amp per centimeter squared, which is fabulous. It's an excellent, very high current density, and that is what makes this alkaline electrolysis so very attractive.
And you do your electrolysis and you get your hydrogen and oxygen, okay, and there are of course ways of completely cleaning up, right, the hydrogen and oxygen. Okay, now another very interesting area which you might want to look at as part of green tech, okay, conceptually, what happens is that you are doing the electrolysis to get what? You are getting hydrogen as a fuel. And what do I do with the oxygen? So what is the difference between oxygen and air? Correct. It's much higher concentration. Okay. So, there's a lot of work where the efficiency of combustion can be improved by using enriched oxygen. Okay. So, ideal green technology would be that I generate hydrogen and I do things with it, and on the other hand, the oxygen which is coming out, I try to use it for improved combustion, and that would make great sense. I hope you are understanding that all of these are coupled concepts. Hydrogen coming out, oxygen used to improve the combustion. Okay, so there's a lot of cleverness, which you can use, and so I want you to look at all this renewable energy, etc., in a much more creative manner. Now that we have covered both hydrogen production by steam reforming and also through the process of alkaline electrolysis, one can do a comparison of the costing of the two processes, and what you will see from this slide is that the costs are substantially higher for electrolysis as compared to steam reforming. In fact, if you look at it at very large scale production of hydrogen, the differential is almost a factor of 5, whereas at if the scale goes down, scale of production of hydrogen, the differential is less, more like a factor of 2. I must of course tell you that this is a rather old slide, almost 2 decades old, and I'm sure that in the last 2 decades there would have been advances in the electrolysis technology, which probably would mean that the differential would not be as large as has been projected in this slide. Another important point to make is that, well, you see, over here we are talking about electricity generation, which is also through thermal processes involving burning of natural gas or coal or something like this, the typical thermal power plant. Now, the scenario could be very different if that is not the case. So, in this particular case where we are talking about steam reforming of methane, or let's say producing electricity by burning natural gas, naturally in both cases you're talking about natural gas, and so the differential might still remain substantial. But then, suppose the two are delinked, as would be the case if, let's say, one derives electricity by photovoltaic, sort of solar photovoltaics. It could be quite different. So that again is something very interesting, and one will have to look out for how these things will really evolve over a period of time. If, for example, the cost of power generation through solar photovoltaics comes down, and if the cost of generating hydrogen from steam reforming using natural gas, let's say if natural gas price goes up, then of course, you can bridge the gap. So this is something that I want you to bear in mind. We will of course be discussing solar photovoltaics in the next lecture, with of course starting with how the entire process of making the silicon solar cell happen, and the dramatic changes, in the cost of panels per kilowatt, let's say, capacity, how it has come down, in the last maybe 60, 70 years, and more significantly in the last maybe 40 years or so. So those are really the kinds of things that make maybe solar photovoltaics and coupled with electrolysis as something to look out for. There is another point which I should mention, that you see, when you are using the normal grid power, you have to use a rectifier to convert the AC into DC. And so that is another huge advantage of using solar photovoltaics, because one generates DC power, so you can dispense with the use of the rectifier. So I think that this is again something that you should make a note of, and so there could be some very, very interesting things which can happen, and which have already happened and are likely to happen in the future, which might make really electrolysis to produce hydrogen much more attractive. Let me also tell you that alkaline electrolysis is not the only way of doing electrolysis. And in fact, this itself is an evolving technology, and it could well be that there could be other alternatives which are superior. And I will discuss that in the next two slides, and then we will close for the day. DuPont has also developed an exactly opposite way of doing it, which is a proton exchange membrane based water electrolysis. Okay, so effectively what they are doing is that they are doing something similar, except that is not done under alkaline conditions. Okay, and they have found a way. It's a very interesting thing that they're doing. You have a membrane, and that membrane is completely solid. Okay, and the electrodes are absolutely snug against the membrane. So it's like a sandwich. You have got two electrodes, and in between you have got your solid membrane, and the membrane itself is your ion conductor. Okay, so I can even use ultra pure water, and carry out electrochemistry because my ionic conductivity is really happening through my membrane. Okay, and you can see ultra pure water is fed to the anode structure of the electrolysis. That's this side, the anode side. Okay, which is made of porous titanium and activated by a mixed noble metal oxide catalyst. Now this is the heart that your electrode must operate more or less at the thermodynamic potential, because if you don't, then you will lose a lot of waste a lot of energy, especially if I try to increase the current density, and if I've got an over potential, then the less will be equal to I squared R thermal losses. Okay, and over potential is equivalent to a resistance. Okay, so I need to be very careful that I operate as close to the thermodynamic potential as possible. Okay, and once I do that, now so here the water is being converted into oxygen, and now I'm left with only H plus. Okay, and it is the H plus that is conducting, right, through this membrane, and it is getting reduced in the cathode, okay, to form hydrogen. You might be under the impression that you can do electrolysis only in a liquid medium, right? It's not true. Okay, you can do electrolysis in gaseous medium. Okay, and for example, I can use steam and do electrolysis. Okay, and so this is a very interesting approach. It is done at a fairly high temperature, 800 to 1000 degrees centigrade. Okay, and at that temperature, what happens is water tends to break down into H2 plus O. Okay, and in the presence of your cell, okay, that O exists in the form of O2 minus. Okay, all right. So I'm basically forming H2 plus O2 minus. Okay, now that O2 minus is diffusing through a ceramic conductor from one side to the other side, and it is getting reoxidized on the other side. Okay, after getting transported, forming oxygen. So I end up forming hydrogen and oxygen, and it is believed that this particular way of doing it is probably more efficient, but nobody has yet succeeded in scaling it up. Whereas all the other things, have been scaled up to very big sizes. Okay, so but you must remember, and by the time another 10 years goes by, technology might completely change. Okay, so what you should be aware of is that there are many options for doing electrolysis. You cannot just say, I'm doing electrolysis.
Is that all clear?
Yes, sir.